Again. Okay, let's continue with the switch capacitor gain stage. Gain stage is just amplifier. Yeah, the transfer function of this amplifier is just this one, right? If this op-amp has a pretty large gain for all frequencies considered, yeah, this resistor will be replaced by switched capacitors. Yeah, so we want to use, this is my switch, by one. We draw the circuit in a single-ended circuit, but you can convert it into fully differential version. Yeah, this ground is actually reference point, 1.65 volt DC. Okay, those switches can be implemented by using just a single transistor or CMOS transmission gate, each transistor, each switch. Yeah, here's my equivalent R1 is T over C1. My equivalent R2 is T over C2. Then my voltage gain will be, yeah, this is just C1 over C2. Okay? That will be my voltage gain over this amplifier. Okay. If you look at this node, you can see we can short them together because see, this node is connected to op-amp virtual ground, inverting input node during by one. Yeah, this node 2. Okay. This node is connected to reference node during by 2 phase, and this node 2. Okay, then we can short them together. So let us see. Yeah, we can short them together. Let's see. Oh, yeah. Oh, actually, we can. So this node is that node. Okay. And we just short them together. But the thing is, see, it should be connected. I need a switch here. During by one phase, it's connected to op-amp virtual ground. During by two phase, it's connected to reference node, right? So I can write it like that. So this is VO. Yeah, this is called switch sharing. Switch is shared. Okay, switch sharing. Oh yeah. So again, this is a gain stage. Okay, gain stage. Yeah, when you want to simulate this switched capacitor, sometimes you get problem with the convergence. So for some simulation, you can use ideal switch. Ideal switch. Do I have ideal switch here? Nope. Nope. Yeah, it's called S. S something, M plus M minus NC control plus NC control minus model. This model name is dot model. This model name SW. And then I have some threshold voltage, and I have on resistance. I have off resistance. Yeah, then say I have, so let's just say, I have a NM node here. This resistance is controlled by this NCP, NCM node voltage. The voltage across this controlling branch controls this switch resistance. So when this voltage is smaller than threshold voltage, then this switch resistance becomes off resistance. When this voltage is larger than threshold voltage, this turns into this on resistance. Okay? So this is kind of MOS style op amp. If you want to change it, this thing is 1 gig, on is 1 gig, this thing is 1K, it's a PMOS switch. Okay? Yeah, you can simulate it. Oh, actually, do we end the simulation? Oh yeah, it's done. Okay, let's look at our simulation result with the ideal CMFB. Whether do I get the same result or not? Oops, I have a similar result, but not good, no good. That's no good. How come? Where is my CMFB? Looks like I made some mistake, somewhere. Actually, Norbert Saylor, did you observe this behavior? I mean, so your circuit works pretty good. Huh?
Yeah, but I have the same problems.
Same problem?
Yeah.
Oh, you got the same problem. Looks like I have some bias problem. Yeah, some bias problem. I have to fix it. Okay? All right. Okay, then let's go to switches. Where is my switch? I have to change it into different folder. Okay, this is a switch, my switch. Let's look at it. Yeah, it has just, I use the current source of 1 amp from 0 to in. I have a voltage source for sweeping, GSW. See, I have my switch SW1, it's in 0. And then through this in node, I will apply DC current 1 amp, DC current. So GSW0, that's my controlling branch, okay? So I sweep this GSW node voltage VSRC from 0 to somewhere, or maybe I change it into 0 to 3.31 millivolt step or something like that, not 1 microvolt. So, yeah, I will simulate it. Let's see. Oh, not homework 5. Yeah, this is node voltage, right? So, yeah, see, because I am flowing 1 amp current, this is input voltage from 0 to, this is 1.65, this is 3.3, and then when voltage is smaller than 1.65, the resistance is a giga-ohm. The voltage becomes 1 gigavolt, right? So let's just change it into log scale. So this is 1 gig, this is 1K, right? So my own resistance 1 kilo ohm when VSW is larger than VT, okay? So my switch works fine. And this is the ideal voltage controlled switch. Okay, any question? Nope. Okay, let's use this switch with the ideal op-amp, okay? So let's look at it. Let's copy this one into PowerPoint. So with a switch capacitor filter, you will come across some convergence problem. Okay, so in that case, for that case, I am trying to use ideal op-amp with the ideal switches. Okay, well, how come this is so complex? Oh yeah, input voltage swing. Oh, yeah. So let's just see. I will. Okay, so here I am using ideal switches and then ideal op-amp here. Yeah, let's look at the ideal op-amp first. So this ideal op-amp is, this is op-amp output node, and this is my reference node, 1.65 volt, and that it's, there is a current flowing GM times IP minus reference, okay? So I have IP is a positive input, IM is my negative input, right? So this part is my op-amp. This is ideal op-amp, right? With infinite resistance. So if I put this resistance here, oops, if I put this resistance there, then see 10 to the 7, 10 to the 7, then DC gain will be only 30, right? Very small. So I didn't put resistance here. If I put resistance, my integrator works in a very strange way. Okay. So how does this circuit looks like? Oh yeah, this is just most switches. Yeah, actually, yeah, this is in is my input. In one is my. So I have a S1 switch here, which works by one. You know, this by one controls that one, and then in one and the where is C1? In one and the rep. Oh yeah, this is actually not that one. I have to use a different one. This is a rep. This is a C1 one pop, and then see I have a S2 switch. This is simple switch by two. So this is what? IP, right? This is IP thing. This is IP. In one IP. S2 should be IM, right? Is it right? IP. IP is connected to IP out. Oh yeah, should be IM. Something wrong. Let me see. This is correct. IP. This is IP rep, right? Negative IP rep. So IP rep. IP is positive. IP is positive. Oh yeah, I think so. This works as a negative input because I'm flowing current that way. So if IP is positive, this node voltage should be negative. So I'm still using negative input. So it should look like that. This is rep, okay? So let's see, this is a straight sensitive switch capacitor filter, switch capacitor integrator, okay? Let's see, it works pretty good or not. Oh, it's almost time. Yeah, actually, I think I have some other circuit. If you look at the, some number 2 or something, it should be straight insensitive, okay? You can find it, okay. Anyway, so this is my circuit. At the same circuit. Don't use voltage controlled voltage source for ideal op amp. Doesn't work. It will take, doesn't take long. So let's just see. Yeah, this is the one. So my output. Yeah, so it works fine, right? It's oh, I am using DC input. DC input. So if you expand this one, so if you put a clock here by 2, oops, somehow it doesn't work. Aha. Yeah, so it settles just constant, settles constant. If you put some MOS switches, you have some droop here because of some leakage. But this is ideal switch, giga ohm, so it's just flat. Okay, and then let's just see what else. Okay. See, if I have some DC resistance here, let's just see R out. Yeah, R out is 10 to the 8. Then my DC gain is this GM times this one is 300, okay? My DC gain is 300, not infinite. Then what happens? Simulate. Then let's see. Where's my out? So there is, the straight line, it becomes a little, there is some droop, right? If I reduce the DC gain, say like to 30, you can see significant deviation. Yeah, there is a very significant reduction of output voltage, right? Okay, question? Nope. Okay, then let's stop here.